Symmetry can be used to determine whether a molecule is polar or not. Let's just review what we mean by polarity. If you have, let's say take HCl. This is more electronegative, so you have a partial negative charge here, you have a partial positive charge here. This is a polar molecule. It has a polar bond. Also, you can look at something like a BF3. BF3 is this structure here. Fluorine is more electronegative, so it takes negative charge away from the boron, and here you have a partial positive charge. However, even though boron fluoride has polar bonds, the molecule itself is not polar. So this is polar bonds, and this molecule is polar. And here you have polar bonds, but this molecule is not polar. You can talk about polarity in terms of a bond dipole. Bond dipole is a vector which points from the positive part of the molecule to the negative part. Here, these bond dipoles will all cancel out. They're of equal magnitude, and they'll all cancel out, so the net dipole moment of the molecule is 0. Now what we want to do is to use symmetry to show whether a molecule can be polar or not. The key point here is that when you do a symmetry operation, that implies that the molecule is unchanged. And what you mean by unchanged also is the dipole moment is unchanged. Now recall the dipole moment is a vector, so even if we have the same length of the dipole but it points in a different direction, then the dipole moment is changed. So a symmetry operation means the molecule is unchanged. It also implies that the dipole moment is unchanged. Okay, so what we do is we look at the dipole moment of the molecule and see whether it's unchanged or not. All right, let's take, for example, ammonia. Here's the ammonia molecule, and it has a dipole moment that is coming out toward you, toward the perpendicular to the screen. Here, the dipole moment points up this way, rotated here. All right, so that's where the dipole moment is. Let's look at these axes here and the planes of reflection. So here's the ammonia is C3V symmetry, C3V, and it has a C3 axis and 3 sigma planes. All right, the dipole moment, maybe you can see, is located right at this intersection of the planes and the rotational axis. So the dipole moment is there. So if you rotate around C3, the dipole moment doesn't change. If you reflect it in any one of these planes, the dipole moment doesn't change. And so therefore, molecules that contain the C3 or C3V symmetry, or in general anything that contains CNV symmetry, can be polar, because the dipole moment does not change when you operate on the dipole moment with every particular symmetry operation in the group. So okay, so C3V can be so a molecule that has C3V symmetry can be polar. In fact, you would say is polar. So let me get rid of can be. Is polar. All right, now let's consider another operation. Let's look at the inversion center, center of inversion. So suppose you had a molecule that had a dipole moment, and now you do the inversion operation. What happens? The dipole moment then points down. So this means that a molecule that has an inversion center cannot be polar, because if it were polar, then the dipole moment would change, and that wouldn't be an element of symmetry. The molecule and the dipole moment cannot change in a symmetry operation. So what this implies is that if a molecule has an I, an inversion center, that means it cannot be polar. And let's look at some other things. Suppose that you have a CN axis and then another CM axis. So you have two different classes of rotations. Now, just like we said for the C3 dipole moment, this implies that one of these axes, say a CN axis, must contain the dipole moment, which will give the symbol mu. But if the CN axis contains it, and then you operate with the CM rotation, which is different from the CN, that means that the dipole moment will change. So CM will change the direction of the dipole moment. So this implies that you cannot have two classes of rotation. Two classes of rotation cannot be polar. Okay, so we've eliminated anything that has an I and anything that has two classes. So let's take a look at the character table, see which ones we've eliminated. Okay, so if we go down here to the D, for example, all the D groups, D2, D3, D4, have two classes of rotation. All the D groups, that's one of the characteristics, or at least two classes of rotation, that's one of the characteristics of the D group. And so, therefore, any molecule belonging to D symmetry, D, DNH, D anything, cannot be polar. All right. Let's look at some of the S groups. S something, Sn, is a rotation followed by a reflection. So let's consider a dipole moment. And so the dipole moment now is coming out towards you. If you rotate that along this axis, but then reflect in the plane perpendicular to the rotational axis, the dipole moment then will change directions. So if a molecule has a dipole moment, it can't have the Sn rotation reflection improper rotation symmetry element. Otherwise, the dipole moment will change, and the supposition is that the dipole moment can't change because it's fixed to the molecule, and the molecule can't change. So this implies that anything that has Sn in it is not or cannot be polar. All right, so if we go back here, all these things that have S's in them cannot be polar, so that eliminates those S's. We've eliminated the D's. Okay, how about the, and we said that the C2V, C3V, all those have both the rotation and reflection planes. They contain a common line along which the dipole moment, so the C2V looks like that's okay. Eliminated the S's and the D's, so these are okay. Let's go up here. How about the horizontal? Go up here. 6, a simple one here. Now the problem here is that you have a center of inversion, or you have separate classes of rotations and so on. So all these C and H are out. We're running out of things to do. And how about these? Well, here you have, for these C6s, or C3 and so on, you have at least two classes of rotation, etc., etc. And if you go through all the character tables, what you end up with is this statement that only molecules that belong to a CN, CNV, or CS point group are polar. Okay, the dipole moment of the molecule must be unchanged by all symmetry operations of the group. So you can go through there. All right, let's do this example. Which of the following molecules are polar, given just using symmetry arguments? All right, so we have to figure out what point group each one of these is in, and yet for that you have to know what the structure is. So let's look at pyridine. Pyridine looks like N, and then there are carbons out here. Looks like a benzene ring, except one of the carbons has been replaced by a nitrogen. All right, so there's pyridine. Pyridine is C2V symmetry. It's just like water, even though it has a completely different structure in terms of symmetry. It's just like water. So as a C2V, this implies that pyridine is polar. All right, let's look at the next one here, nitroethane. Nitroethane, C, there's an H, and they got two H's up here, and then you got the nitro group here, double bond O, not quite sure the single double bonds. There it is. What symmetry does this have? This has C1 symmetry. C1 symmetry is a Cn, where n is equal to 1, so therefore this is polar. Let's look at mercury bromide, HgBr. This is a structure, it's a linear molecule. And what point group does that correspond to? That corresponds to a D infinity H. So if we look up D infinity H in our character table here it is, D infinity H, that has an inversion center. If something has an inversion center, it cannot be polar, so this is not polar. All right, so that's how you can use symmetry in order to determine whether a molecule is polar or not.